Do you want to learn how to perform 2D navigation with a drone? Then stay with me. This video is for you. Hello ROS developers and welcome to the ROS questions and answers video series. If you want to learn anything about ROS, this is your channel. ROS navigation, ROS with drones, ROS for autonomous cars, everything about ROS is here. Learn ROS step by step and push your ROS learning in just 10 minutes of video. I am Alberto, and as I've said in the introduction, today we are going to be talking about a special topic, which is drone navigation. But before anything else, remember to visit our Robot Ignite Academy, our online academy where you will find practical online ROS courses using simulated robots. No installation required. You will find a link to the academy on the video description. And now let's start with the video itself. So, as I've already said in the introduction, today we are going to be discussing a special topic, which is drone navigation in 2D using the navigation stack. So lately we have been receiving some feedback comments like this one from this user who says, "Hi, I have a question about using navigation stack on drone indoor navigation, fixed altitude 2D navigation. Since I have a project trying to navigate indoor with built-in map, the SLAM part has already done so far. I'm wondering if it's possible to use the path planning and obstacle avoidance part in move base node." Okay, so basically this user, he continues, but he basically wants to know how to apply 2D navigation with the navigation stack to a drone indoor environment. And this is what we are going to be doing today, and in probably a couple of videos more. Today we are going to be covering the mapping part in this first part of the video, so how to create the map. And yeah, so let's go. I'm going to start as always in ROS.js, in the ROS Development Studio. And here I'm going to create a new project, which I'm going to call Drone 2D Navigation. Let's create it, and let's open our project. And meanwhile, I'm going to be looking for the Hector Quadrator simulation. I'm going to use the one from the construct, the one that we have created. Okay, I don't see it here. Let's go to the public simulations. Okay, here we should have it. And Hector, where are you? Here it is, Hector Quadrator Sim. Okay, here we have it. Let's go back to our ROS.js environment, which has already been loaded. So here I'm going to open one shell and one IDE to start. So let me go to the simulation workspace where I'm going to place my simulation. So I'm going to clone this repo here. And I'm going to compile it. There we go. I will put all these links in the video description so that you can follow the video while you are looking at it with me. So don't worry about this. Then, yeah, let's start opening another shell where we are going to be starting RVs. And yeah, so let's wait a few moments until our simulation compiles. It shouldn't take too long, but meanwhile let me start RVs. I'm going to open as well graphical tools here. Let's move it to a new window to visualize it better. There we go. Oh yeah, okay, so I haven't started yet the simulation, so it's complaining. So we will wait a few seconds until our simulation compiles and we can start it. And I will resume the video when this has finished. So see you in a few seconds. Hello there again. So we have finished compiling our simulation. That's great. So now what we are going to do is to source our workspace, of course, and I'm going to start the simulation directly. So I'm going to use the camera launch from the Hector Quadrator Gazebo package. There we are. So this will start the ROS core and our simulated environment. So yeah, now I will be able to start RVs. For instance, here I have it. And let me open as well another shell to check a little bit the simulation and the topics I have available. So if I do here a ROS topic list, I will see a list with all the topics I have here in this simulation. As you can see, I have many topics: altimeter, command bell in order to move the drone, to control the velocities, camera, front camera, and here I have a topic which is called scan, and this topic basically is publishing the values of the laser. So let me do here a ROS topic echo of this topic. And well, as you can see here, we have many data being published, but basically these are the readings of the laser. So this is everything that the laser is detecting, and we have this in the topic called scan. Yeah. So as you may already know, in order to perform 2D navigation, we need a laser data. So in this simulation, I already have it provided here in the scan topic. So in case you already have laser data, perfect, you can move on. If not, it's possible that you have a Kinect camera, for instance, or a 3D camera, then you might want to use this package, depth image 2 laser scan. It's not here. Okay, depth image 2 laser scan. You have this package available, which basically will convert your depth images, which can be captured with an ASUS Ixion, a Kinect, or whatever, into laser data that you can then feed into the navigation stack. Yeah. So yeah, well, in our case, we already have the laser data, so we are good to go. And yeah, I have my simulation here, as you can see, with the Hector Quadrator here, and a very big environment here, which we are going to use to navigate. And yeah, so the next step will be to create our mapping launch to start the gmapping node. So let's go to the Catkin workspace, and here I'm going to create a new package, which I'm going to call Quadrator Navigation, for instance. There we are. I will have it here. Quadrator Navigation, here I have it. Then I'm going to create a new folder here for the launch files. Let's refresh this. There we are. And well, super easy now. What I'm going to do is to basically go to the Turtlebot navigation package, to the launch folder. Here I have it. And to the gmapping folder. As you can see here, I already have it here. If you don't have this package, you can look for it as well in the ROS wiki. You have it here, Turtlebot navigation. And basically what I'm going to do here is to copy the gmapping launch, which is this one, into my package. So into the Catkin workspace, SRC, Quadrator navigation, launch. So now I will have it here. There we have it, great. Let me rename this to I don't know, Quadrator mapping.launch. Okay, that's good enough. So there we are. So basically what I'm doing here is to reuse the gmapping launch for the turtlebot for my drone. Then basically what I will need to do is to verify that these topics and frames are correct. So here basically I'm using the scan topic. So this is the name of the topic where to get the laser data. I will need a base frame, which in this case it's using base footprint, and as well I will need an ODOM frame. So for this we know that our laser data is published into a topic, do you remember, named scan. Yeah? Let me do it here. So our topic where we have the laser data published is scan. So here we can already modify this to fit our simulation, our drone. Then now for the frames, what I'm going to do is to get frames tree of my simulation. So I can get this by running this command, rosrun tf view frames. This will generate, in this case in the Captain Workspace SRC, because I'm executing the command here, this will generate a frames tree of my simulation. So it will generate a PDF file, as you will see right now. Let's refresh this. Here I have it. So now I'm going to download this file, and here I can see the frames tree of my simulation. Here I have sonar link, the laser link, the camera link, and as we can see, you have the base footprint as well, which is the base frame of the drone. Let's check it here. It will be clearer. So let me add here a robot model to see my drone. And TF display as well, which is here. And let me here show the frames. Okay, there they are. I'm going to select only the base footprint, base link, and the world. So let me now uncheck this. So as you can see, the base footprint, base link out, okay, so the base footprint is here in the base of the drone, as well as the world frame. And the world frame is a frame that represents, it's a kind of a substitute of the odometry frame. So here obviously in the drone we don't have wheels, we don't have encoders, so we don't have an ODOM topic as it is, but this world frame is the one that we're going to use as odometry frame. So we can put this into our launch file. So the ODOM frame will be the world frame, which is this one here, and the base footprint we can leave it as it is because we also have this base footprint link. So yeah, we have the scan topic of our simulation, we have the base footprint frame and the world frames as ODOM frame. So we are ready to go, basically. So now what I'm going to do is to launch my package. So ROS launch, quadrature navigation, and quadrature mapping dot launch. Let's start it. Okay, there we have it. Great. So now let's go back to RVs, and well, here I can take out the TFs for now, and I'm going to switch to the map frame in order to visualize my map, and I will add laser visualization, which I have here, and a map visualization as well, in order to visualize the map I'll be generating. Let's also add again the robot model. And for the laser scan, I will select the topic, which is scan. There we have it, and there we can see the laser readings. And for the map, I'm going to select the topic, which is map. And I will start seeing the map generated. Here I have it. Excellent, so, well, that's it basically. All I need to do now, well, let me first of all save the configuration so that I don't have to do this ever again. So I'm going to save it here. I'm going to create a new folder named RVs, and I'm going to save this configuration as mapping. There we go. And all I have to do now is to move the robot in order to start building the map. So for that the topic I use to move the drone is command vel. So I can use any program that writes into this topic. For instance, I can use the Touchable keyboard, which writes into the command vel topic. There we are. And let me put this a little bit bigger to visualize it better. And now all I have to do is, well, first let me take off. I will need to take off the drone. I can do this by publishing into the takeoff topic. There we have our drone taking off. And now, yes, I can start controlling it. So let's launch again the keyboard teleop program. There we go. Okay, so let's move forward. Okay, so there we have our drone moving. I can control it perfectly. And as I move my drone through the environment, I can check here. Let's move it a little bit more. There we go. As I'm moving my drone, the map will start to be generated here. So let's head to this room, for instance. There we go. Let me see better in another angle. Okay. Let's see if I can pass through that small space into that other room. Yeah, I think I will fit. Let me see. Let's move a bit forward. Okay. Yeah, there it's going. So now I am already here in this new room, as you can see, and here in the map, as you can see, I have left the first room and I am entering this new room, which is now starting to get mapped. So yeah, that's it. You can move your robot wherever you want, build a map as big as you want. Obviously, I don't think it will be a good idea to create a full map of all this environment because it's huge. But well, you can build the area as big as you want. in order to later be able to send goals and move the robot around all these rooms. So yeah, that's it for the video of today. I hope you liked it. In the next video we are going to create the localization system using AMCL for this drone. So yeah, see you in the next video. If you liked the video, remember to subscribe, to leave a like, leave your comments in the comments area below. Anything you want, any comment in order to improve is welcome. So yeah, there you are. See you in the next video. Goodbye.